Welcome back to the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. Today we're doing multivariable calculus. We're in Chapter 1, partial derivatives. We have extreme values and saddle points, section 1.7. And this lecture we're going to do the second derivative test and some examples. And we're going to do some of the same examples as last time to match that we're basically doing. We have the first and second derivative test for functions of one variable. We now have first and second derivative test for this. Now we're going to use the second order partial derivatives. Let's do it. All right, what the second derivative test tells us is, suppose we have a function of two variables where we have continuous second order partial derivatives on a disk centered at our point A, B again. And we're going to assume that we have a critical point already, or that our first order partial derivatives are zero there. Then what the second derivative test does is it does an analog to what it does for functions of one variable. It tells us whether we have bumps, which are local maxes or local mins, or whether we have saddle points, whether they're neither local max mins. And because we're in a slightly higher dimension, we've got one more condition where we can't tell in the test. But rarely, especially at first, am I going to give you the scenario where this guy is zero. What does that tell us? First of all, this guy right here, I'll write down in a second, is called the Hessian or the discriminant. What that does for us, it's actually a 2x2 determinant, so I'll show you how to memorize how to get that in a second. So if you're like, oh, I'm not going to memorize what that formula is, I'll give you a clever 2x2 determinant business for it in a second. And then we're sneaking in even more linear algebra into the multivariable calculus class. If I have, first of all, that the second order partial derivative with respect to x, or fxx, if that is less than 0, and I have that the Hessian is positive, then I have a local maximum at that point. If I have that the second partial with respect to x is positive and the Hessian is positive, then I have a local minimum. What that's saying basically is that if the Hessian is positive in either case, then my function, the curve goes all the same directions, up or down in all directions. So it's going to be a local minimum or a local maximum. If you have, it will go in the same direction as fxx. If you have that that's less than 0, you're going to have a maximum. And if you have that that's larger than 0, you're going to have a minimum if the Hessian is positive. If the Hessian is negative, we immediately get that we have a saddle point. And if for some unlikely reason you get that the Hessian is 0 at that point, you're going to have to use some other technique. Because this is inconclusive, you can't use this second derivative test. You can go back to the first derivative test or something like this to try and assess in our steps of using the first derivative test, finding when the partial derivatives are 0 and finding the critical values and doing all that kind of business. You'll have to go back to that scenario or something else, because we do have a scenario where if this is exactly 0, you can't use the test anymore. Be careful. It has to be positive or negative. Let's give it a nice expression for the Hessian, just so that we can organize this, and then we'll apply it to some questions. The Hessian or the discriminant, we're mimicking the terminology for the quadratic. The discriminant is the thing underneath the square root. Right now, what this is, it discriminates based on whether we have a minimum or a maximum or a saddle point or inconclusive. So that's why they called it discriminate. What is it? Basically, it's a 2x2 determinant. If I put the second order partial derivatives in as 2x2 matrix, and I take the determinant of that, I get fxx times f. This is AD minus BC in determinant theory, but we get these specifically, which are the mixed partial derivatives. By Clairaut's theorem, fxy equals fyx, and so I can put squared, and that's where they're getting this fancy fxx fyy minus fxy squared business from. Really, if you want to memorize it, it's the 2x2 determinant. These calculations are the same, so compute whichever one you want. We're going to do it in a second. But if you get that the discriminant is 0, this is inconclusive. If you get that the discriminant is less than 0, you have a saddle point automatically. Remember, you're going to be working backwards from, given the function, you have to calculate all these things. So first, what is my most efficient algorithm to do this? First, I'm going to compute the first partial derivatives, and then they have to be 0 at the point. That's step one, because that's what the algorithm said. If your function is, all these things are continuous, and that you have that the first order partial derivatives are 0 at those points, then you can do this discriminant business. So step one is compute the first order partial derivatives and make sure there's 0 at the point you're looking at. If that happens, then I have to compute all of the second order derivatives, and there's 3 of them: fxx, fyy, and fxy equals fyx. Then you compute those, and then you're going to have to compute the discriminant, which is the multiplication and subtraction of those things at that point. And if you get 0, you're back to square one. If you get less than 0, you have a saddle point immediately, and if you get positive, then you have to check fxx, whether it's positive or negative, to find out whether you have a maximum or a minimum. Let's do that. Example 1, find the local extreme values of the same function we did in the previous video. We have a function x squared plus y squared minus 4y plus 9. We want to find the local extremes using the second derivative test now. What are we going to do? 1. First of all, I still need the first derivatives, first order partial derivatives. So fx is going to be 2x and fy is going to be 2y minus 4. We need the critical points. So when are those 0? Fx is 0 if and only if x is 0. And we did this in the previous video, go watch. Fy is 0 if and only if y is equal to 2. That gives us the only critical point, which is 0, 2. From that, now, I need to start running. This is a critical number, which says my first order partial derivatives are 0 there. Now the second derivative test says you have to compute the discriminant and fxx. If the discriminant is negative, you have a saddle point. If it's 0, it's inconclusive. If the discriminant is positive, then you have 2 cases. You have a local max or min. If the fxx is negative, you have a maximum. If it's positive, you have a minimum. Let's assess that. What do I need? I need fxx, which luckily is 2. Good. I need fyy, which is also 2. Then I need fxy or fyx, it doesn't matter which one. Fx with respect to y. What does that give me? 0. I like that for my calculation. Remember, that's also equal to fyx if you really want to go the other way, they're the same. Now, because it was so nice and they're constants, we don't even have to plug anything in there because they're constant values. But what that says now is we want to run case 1, d is now equal to fxx times fyy minus fyx squared, which is going to be 2 times 2 minus 0 squared, which is 4. That's always greater than 0. It doesn't matter what point we have because it's a constant, so I knew the discriminant was going to be a constant function in x and y. So the discriminant is positive. What does that mean? It means we have not a saddle point, we have either a local max or a local min. It was a local minimum. Watch the last video. So now what do we have to get? Then we look at fxx, and that is equal to 2, which is always positive. So we have those 2 things. We have fxx is positive, and we have d is 4, which is positive. And those 2 things tell me I have a local minimum at 0, 2. That's exactly what we found last time. This has to be the only minimum or maximum because we only had one critical value, and we also showed that our function was always larger than 5, which is the value at this point. So this is actually an absolute minimum as well as a local minimum. Next question. Example 2, we're going to find the local extrema of this function now, xy minus x squared minus y squared minus 2x minus 2y plus 4. It looks like a hyperbola minus a circle or something like this, but now it's a function of 2 variables. What are we going to get with this? First of all, we look, and technically, what am I doing? The domain is all of r squared, and because it's all of r squared, there's no boundary points. You could also possibly have local extrema at boundary points on your domain. We're not really going to get into that. We're going to focus on interior points. But my domain is R2, which has no boundary points, and therefore there's no extreme values. And what that says quickly is the only place I could have extreme values is where my first order partial derivatives are 0. Therefore, I compute those. Fx now is going to be equal to y minus 2x minus 2. And y is going to equal x minus 2y minus 2. When are these equal to 0? These are equal to 0 if and only if what? This is a linear system of two equations and two unknowns. Rephrasing that, and I'm going to rearrange it, I have a 1 there. So that gives me x minus 2y equals 2. And then I have negative 2x plus y equals 2 is the linear system I get. I augment the matrix. You can solve this however you want. I'm going to augment the system. I get 1, negative 2, 2, negative 2, 1, 2. Multiplying this row by 2 and adding it to this row gives me 1, negative 2, 2. I get 0. We get negative 3. And I get 4 plus 2 is 6. That immediately gives me that y is equal to negative 2 or negative 6 over 3. And then I get back substituting, that gives me x is negative 2 also. I skip steps also, but at least I showed you what they're doing. I have to solve a 2 by 2 system. Doing that, I only get one critical point, negative 2, negative 2. Long story short. So what they're doing most of the time is saying this. Therefore, p is negative 2, because x equals negative 2 and y equals negative 2 is the unique solution to that 2 by 2 linear system. Having that now, this is our only critical value, and we can only have extrema at critical values, so we have to check now using the second derivative test. What are we going to compute? We have to compute all the second order partial derivatives and then evaluate them at the point negative 2, 2 and see whether the discriminant is positive, negative, or 0. Then if it's positive, we check fxx and see if it's positive or negative to get the max or min. The discriminant is fxx fyy minus fxy squared. I remind myself every time I want to know if that's positive, negative, or 0. I'm hoping not 0, otherwise inconclusive. What I need for that is fxx, which is going to be now the derivative of this guy, which is going to give me negative 2. Oh, so he's immediately less than 0, so it's a maximum if it's going to occur. Then if I have fyy, that's going to give me, what am I going to get? Also negative 2. Then I'm going to get fxy is going to be the derivative of this one with respect to y, which gives me 1. Oh, so that discriminant is positive. I can see it. I'm calculating already. What does that tell me? Therefore, we got constants again in this one. We'll step up our function a little bit more in a second. But for this one, we get, this is negative 2 times negative 2 minus 1 squared, which is 4 minus 1, which is 3, which is positive. And fxx is negative 2, which is less than 0. So we have a local maximum at this point. Next, I'm drawing the pictures ahead of time so you can see. Hopefully from the picture you can see we're going to have 2 critical points in this one, and then it turns out we're going to have a local maximum at one of the points, and we're going to have a saddle point at 0, 0, and we're going to have a local max at 2, 2. It turns out this is also 2. So at 2, 2 we're going to have a local max from the geometric avatar of this surface S, and it looks like at 0, 0 we're going to have a saddle point. Now let's use the calculus and the second derivative test to show that the picture isn't lying to us. What do I need? First of all, I need the first order partial derivatives. That's going to give me, in this case, the derivative with respect to x, in this case, is going to give me negative 6x plus 6y. And fy is going to equal 6y minus 6y squared plus 6x, and I take these partial derivatives. Now what do I have to do? Again, I was supposed to check and find my domain, but we're getting used to this, so I'll quickly say it. This is a polynomial of 2 variables. This domain is R, therefore there's no boundary points, therefore the only place I can have critical values is when the first order partial derivatives are 0. Therefore now, we have to solve this nonlinear system in 2 variables. How are we going to do that? Luckily, we won't give you anything too complicated, so you start stealing your ideas from me, which I stole from a couple books, and we go from there. From the first, so now actually I have 1 and 2. I have 2 equations. From those equations, I see from 1, luckily, x equals y. Whew. I can get rid of one of them. What that says is 6x equals 6y, and then I can invert the 6, and I get x equals y from equation 1. Just like in linear algebra, when you have two linear systems, sometimes when it's two variables, I use the first one to find out information about them, and then I plug it into the second one. I'm doing the same thing now, but it's a nonlinear equation in the second equation. That means from the second equation, I can plug that in there, and what does that give me? That gives me 6x minus 6x squared plus 6x equals 0. What does that give me? I can group these together. That's going to give me 2 times 6x minus 6x squared equals 0. I'm factoring it already in my head. I've got two groups of 6. But what do I have in both terms? I have a 6 in both terms. I have an x in both terms. Factor that out. I have 6x, and then I have 2 minus x equals 0. That tells me that 6x equals 0, or 2 minus x equals 0, and that will give me x equals 0, or x equals 2. And the first equation tells me y equals x, so that will tell me y is 0 and y is 2 also. So I get, oh, already, at least in the picture it's matching, I got the 0.00 and I got the 0.22. Now let's find out what happens there. At these two critical points now, what I'm going to check is the discriminant. fxx is equal to, oh, I erased them. I now need the second order derivatives of these guys. So fxx is going to be -6. fyy is going to equal 6 minus 12y. And fxy or fyx, whichever one you want, is going to be, if I take the derivative of this one with respect to y, I am going to get 6. Therefore, now we finally have one of these which is still a function of x and y. So now you have to evaluate them at the point 0, 0, or 2, 2. We didn't have to do that in the previous examples because we got constant functions because our functions were fairly simple, so the first and second order partial derivatives became numbers eventually. Now what do we need? At 0, 0, we have fxx of 0, 0 is still a constant, -6, but fyy at 0, 0 is equal to 6 minus 12 times 0, which is 6. And fxy at 0, 0 is equal to still 6. And what is that going to give me? That tells me that at 0, 0, the discriminant d is fxx at 0 times fyy at 0 minus fxy squared at 0, which is these numbers now. So that should be -6 times 6 minus 6 squared, which is, I don't even care, less than 0 is what we need from that. This is definitely -36, minus 36 is -2 times 36 is -72. Okay. -72, which is less than 0. That's all I wanted it for. That says the discriminant is less than 0. I don't even have to compute anything else or think about that. When the discriminant is negative, saddle point. So that means 0, 0, f of 0, which is also going to be 0, is the saddle point for that curve right there. There it is. For the second point, at 2, 2, I now, again, fxx is still going to be -6 because it was constant. Fyy, I have to compute. Fyy at 2, 2 is going to be 6 minus 12 times 2, which is 6 minus 24, which is -18. And then I need fxy at 2, 2 was also a constant, which will be 6 still. That tells me now the discriminant at 2, 2 is equal to fxx at 2, 2 times fyy at 2, 2 minus fxy squared at 2, 2. That gives me -6 times -18 minus 6 squared, which is, this is 6 times 6 times 3 minus 6 times 6. They have two 6's in both, so I can take 6 squared out, and that gives me 3 minus 1, which is 72. 36 times 2. Yeah, I like to do arithmetic, but either way, I got, what does that say? Positive. So the discriminant is positive 72 this time. Therefore, what do I get? The discriminant D is positive, and fxx was negative. Therefore, we have a local maximum at that point, and that's exactly what it says. At 0, 0, 0, we have a saddle point, and at 2, 2, the point 2, 2, f of 2, 2, which is going to be some number, gives us a local maximum at that point. Next time what we're going to do is we're going to do more problems with this because it can get out of hand, and we need to try a bunch of different scenarios when we have to find conditions on, like when the first order partial derivatives are 0, that can give us non-linear equations in two variables and stuff like that, and then that can get crazy, so we need a bunch of practice. So our next video will be more and more examples of the first and second derivative test to find local max, local mins, and saddle points for functions of two variables. Please subscribe right here, hit the notification bell. You'll get notifications for this series and a bunch of other ones. See you next time.